Hi again. So I want to do a couple more examples of hypothesis tests. We did example 5 in the last video, and example 6 I'm going to skip. You can use this for practice if you want. And at the bottom, it does have a section on checking work with calculator. So some of you may have graphing calculators, one of the TI calculators, and this is another theoretical calculator. So just like the GeoGebra, where I showed you on the GeoGebra theoretical calculator, the TI calculators do the same thing. So you are welcome to use those as well if you have it. Of course, if you don't, use the GeoGebra one. The only thing that's trickier about the TI is it's harder to get a screenshot if asked for, but you could just write what you got from the calculator. Okay, so if you'd like to do another example, try one on your own, I would try this one. And then I'm going to do the next page, this A and B. And the reason is I want to do a variety of different types of tests. And then I'll save the last page for us to practice in class. Okay, so if you want to practice one on your own, use example 6 and then save. We'll do page 5 together, save page 6 for class. Okay. Okay, so this one says two-tailed test. How would the previous problem change if we thought the actual value was different? So this is the one related to the one we just did, where Time Magazine said 33% of all cars sold in the US are SUVs. I want to show what happens if it says, instead of a direction, it says different. After some investigation, it appears the actual value is different. Suppose a random sample of 500 recently sold cars shows that 145 are SUVs. Okay, so I'm not going to write out everything because we just did the entire test. I just want to write out what changes for a two-tailed test. So remember, different is not equal to because it doesn't give us a direction. So I'm going to rewrite out the hypotheses. Our null would be the same, p is equal to 0.33, but our alternate is p not equal to 0.33. Okay, and here's the one we wrote out before. So instead of a left tail test, this will be a two-tail test. I guess it says that right there. Doesn't hurt to write it again. Okay, our conditions would be exactly the same. Our p-hat, our z-score are all exactly the same. The difference is with our p-value, okay? So the difference is our p-value, because we're not just going in one direction, we need to look at both tails. So it's actually going to be 2 times, and I'll show you on Staplet, 0.0286. For a two-tail test, it doubles our p-value. 2 times 0.0286, which is 0.0572. Okay, so let me go back to Staplet. Normal distribution. I still have this one here. So essentially, instead of only being concerned about evidence that was on the lower side, we're also concerned with evidence on the higher side. So I'm just going to draw a little graph on our paper. We could do outside of a region, and then you'd have to put in both. What you would do is put in the positive and the negative. So that is another way to do it, rather than multiplying by 2. I do negative 1.9022, and then 1.9022. And then that shows me that the double the region. You don't have to do that, though. It's up to you. Some people like the visual, which I think is great. So let me just draw a little graph over here. This is our standard normal, 1, 2, 3, 1, 2, 3 standard deviations. So this is a little less than 2 away. Less than 2 away, and of course my drawing isn't quite symmetric, but this is our p value on both sides. Okay, sometimes that changes the decision, right? So remember, you're supposed to set all this up before you actually collect your data. You can't be like, oh, well, my numbers were less, so I'm going to choose a left tail test, right? You have to specify your direction before you start your test. This actually does change the conclusion because it's now over 0.05. So this also lets us write a different conclusion. So 0.0572 is greater than 0.05. So now this is not significant. Almost seems like there should be a different alpha for one tail versus two tail test. But remember, you're specifying all of that when you set up the test before you gather your data, okay? Okay, so let's go ahead and write our conclusion. So this one's going to be worded a little differently. We're going to say with a p-value of 0.0572, we fail to reject the null hypothesis. We do not have evidence or enough evidence that the percentage of all cars sold in the U.S. that are SUVs is different from 33%. Okay, so with this being over this threshold of 5%, we're saying, well, getting that result is reasonably likely due to chance. So it's probably just sample to sample variation versus a significant difference. Okay, so keep in mind with a two-tail test, it is harder to get a significant result. And that's because you're not specifying a direction beforehand, so it's kind of a trade-off that way. Okay, so that's an example of a two-tail test. Let's do one more test. And we've only got half a page here, so we'll have to kind of squeeze it in to this space here. Let's go ahead and read it. Census.gov claims that 29.7% of students work full-time. An informal student survey at PCC shows that 18 out of 68 students worked full-time. Test the claim that the actual proportion is higher than claimed. Okay, so we've got a higher here, so that's giving us our direction. Let's write, we could write the P0 if you want to, and then our P hat is going to be 18 out of 68. Okay, let's write our hypotheses, and I didn't write the letters up above. I'll write the letters on this one again. So our claim, our null first, is that the PCC number of students that, or proportion of students that work is the same as what census.gov says. P is equal to 0.297, so we're going to change that to a decimal. And then we're testing the claim that maybe at PCC students work more than that. Or more students work full-time than that. So higher than claimed would be HA is P greater than 0.297. So this is a right tail test. Okay. And be really mindful of my space here. So I'm going to write my conditions over to the side, over to the right-hand side. Let me find my sheet again. So we wrote out our hypotheses, check our conditions, independence. Okay, so this is independence and randomization, or how we get our sample, right? We need a random sample, but we need to look out and make sure we don't have any bias. So independence, We need to make sure students are independent from each other in how much they work at their job, right? Students. And how much they work. Okay, for example, I also teach online classes, and many of those students work full-time. And then they do the online asynchronous classes because they can do their work in the evenings and weekends and late at night and whenever they're able to. And I really admire that. So we wouldn't want to oversample online students. And not all online students work full-time. Some are full-time students as well, and maybe don't work out at a job right now. So we just want to make sure that we have an unbiased sample, a representative sample of all students, right? So we want to watch out for like online students. We need to look at maybe time. Let's say we oversampled evening classes, or I know you can work full-time and work evenings and weekends as well. So we just want to make sure we get a representative sample, okay? So watch out for oversampling online students, evenings, etc. Okay? Even though I know I've had a lot of people who work in the medical field, and some people work nights and then come to class during the day. So just some things to look out for. And then we need a random sample. Okay, does it say that? An informal student survey. Ooh, okay, so we want to watch out for voluntary bias here as well. So we need a random sample. Okay. Now, it's okay if you tell me that you don't think the conditions are met on any of these questions. We're still going to just do the whole problem. I would never try to trick you and say, oh, you shouldn't have done this problem because the conditions weren't met. I just think it's always good to be mindful of the fact that we're meeting the conditions so we can actually calculate a p-value with our normal distribution. Okay, so this informal, I'm a little suspicious there, right? Is this one instructor, asking all of their classes? Is it more a convenient sample? Is it a voluntary sample? So just want to raise a red flag there. Then we are going to do our next condition, which is large population. Let's see, let me underline these because they're running together. Large population, or large pop, 68 PCC must have 68 times 10, 680 students or more. Yes, I'm sure of that one. That's great. And then success failure. Okay, this makes sure that our distribution isn't skewed. Okay, so we use our null, so 0.297 n times p0. We have 68 students times 0.297. Let's see what that's equal to. And we can round this, it's fine. 220, it's clearly over 10. Let's do 229, approximate. 229, and then in Q0, 68 times 1 minus. Pretty sure that's also going to be Yeah, that's about 48. Okay, check those off. Those are both greater than or equal to 10. Okay, great. So conditions, okay, we're not too sure about this random sample or not, but we're going to keep going. Anyway, and letter C is write the observed statistic and calculate our test statistic Z. Okay, so p hat, I already wrote it there, but I need to divide it. 18 out of 68, which is 0.2647. Okay. Our other one only had 2 digits, which is nice. If it has more, we're going to use 4 as our standard. That's the way my open math questions are coded. So 2647. Okay, that is our p hat observed statistic or sample statistic. It comes from our sample. And now we're going to use our z star, or not z star, our z score. Z is equal to p hat 0.2647 minus p0. We want to know how far away is this? 0.297. Wait, this is coming out less. Hold on, let me pause for 1 second here. Okay, well, I double checked everything, and this is an unusual problem. Usually we wouldn't see this because this is definitely going to fail, right? Because if they're saying that the actual proportion is higher, we usually would get a sample. In order to have evidence for that, it's got to be actually higher. But this one's actually coming out lower, okay? So let's just continue for practice. It's good practice. And then we will, I'll make some notes on here. Okay, so I've got the p hat minus p0. Now I need to do the square root p0 q0 over n. I'm going to save lots of space here. So we've got 0.297 parentheses 1 minus 0.297 all over n, which is 68. Let's figure out what this number is. 0.2647 minus 0.297. I'm going to hit enter, or you could use parentheses around the top, divided by the square root. Oops. Let me start over. Divided by the square root of 0.297 parentheses 1 minus 0.297 close parenthesis divided by 68. Okay, so I'm getting negative 0.5829. Okay. So this could happen in real life where you just guess the wrong direction, right? But it often doesn't happen in stats questions, because usually on a right tail test, you'll end up with a positive z-score. On a left tail test, you'll end up with a negative z-score. If it's a two tail test, it could be on either side, okay? So this is definitely going to fail because it's on the wrong side, but it could happen in real life. Okay, so we have found our z value, and then we're going to find our p-value. So our p-value, go this way, is the probability, and we're testing higher, so we're going to go z is greater than negative 0.5829. We've if our conditions are met, which is a little questionable, we're going to go to our normal distribution. I'm going to reset this. We're finding an area, which is a p-value. Z is 0, 1. And we are going to the right. What's going to happen is this is going to be over half. Usually we're going towards the tail. So negative 0.5829. Yeah, so if this happens, just double check that you're going in the correct direction, because if it's going in the direction of the test, it'll be less than half. It'll always be going towards the tail. But because this one actually came out the opposite of the direction it was supposed to, it's coming out with 0.72. So this fails very badly. 0.72. Okay, so that means it's very likely to get this value under the null hypothesis. Okay, so it's not significant. So that would be step D, technically. 0.72 is greater than 0.05, so this is not significant. Okay, we write our conclusion, which is E, with a p-value of 0.72, we fail to reject the null. We do not have evidence that more than 29.7% of PCC students work full time. Okay. Okay, so remember, we could check that on our theoretical calculator, either the GeoGebra one or the TI one. I also want to do a stat key real quick. Give you a little more practice with that. Okay, I'll put the link in here for you. If you Google stat key, it comes up pretty quickly. And we are doing hypothesis tests, so we would do a test over here. We're doing a test for a single proportion. And so there are two things we need to edit. We need to edit our null value and our p-hat, essentially. So I'm going to put our null value of 0.297 in here. And then that will be the center of our distribution, and then I need to put in our sample, which was 18 out of 68. So 18 and 68. And let me make this just a little narrower so you can see it. Okay, right, so your p-hat will always be called your original sample over here, 18 out of 68. And notice they only do 3 decimal places. So when I divided, I got 0.2647. That's the same as 0.265 by rounding to 3 digits, okay? And then in general, we're going to do 2,000 samples. So you could do smaller combinations if you want. I'm going to hit 1,000 2 times. And if we had a random sample, notice this is roughly normal, so that is good. And then we are doing a right tail test, so we would click on right tail. And then we're going to put, make sure that's in the window. We're going to put our original sample in this right tail box at the bottom. So I'm going to put in 0.265. Well, I'm just curious what happens if I do 2647. looks like it just takes it to 3 anyways. Okay, so, and this, because it's on the left side of the null, it's less than the null value, it's over 0.5 again. So we get 0.76, so that's fairly consistent. We got 0.72, and remember, if you redid this, you would get a different result each time, but it's fairly consistent with our result. So if a question asks you to do a simulation, you would do it that way. So let me just write that down. Our simulation. P-value or simulated p-value was 0.7. What was it? 0.76. Okay, great. And then I just want to show you, even though it's not the same problem, on the note reference sheet, I've got an example for you here. So let's just write down the things you need to, or circle the things you need to enter. You need to put in your null value right here, and then you need to edit your data, and that's where you put in your p hat, and this also shows you your p hat right there. And then you're going to select the type of test, right? And then depending on which one you put in, you get these numbers at the bottom. So whichever one you put in, or if you do two-tail, it'll give you both, right? And then you need to see, where does this fall? Does it fall in the upper side or the lower side? Because if you don't get it on the right side, it'll get confused. So this is our p hat, and this is this particular one was a left tail test. So I put it in on the left, and then this is our p-value. Okay, so I hope that gives you an example for simulation, and I will see you in class, and we'll practice some more when we get to class. Okay, see you then.